there will be no need for conferences. There will be no chance to work somewhere abroad, because people will not communicate with you. And if you do not know how to write in English, it will be very difficult to publish your work in readable form. The lectures of today are recorded, and it means if you have problems understanding what people say, there will be a chance to re-listen to the lecture. I can translate them and help you with the text correctly. But for this day, having talked to many of you, we realized that at least half of the students are happy with this English, to uninterrupted English, and for the rest, it's also very useful to exercise listening and get used to real. And also they are saving time. The call is this.
Thank you, Elena. Good afternoon, everybody. So most of my career, I've worked in synchron radiation, starting from when I was a graduate student. I'll talk a little bit about how I got interested, because it was in effect done close to when I was your age. Some halfway through my career, there was a synergy obvious from what we were developing with the synchrotron X-ray Lowry diffraction, with improving a lot use of neutrons at the nuclear reactor. And that synergy I will also try and bring out, both in terms of methods and the complementarity of the X-rays and the neutrons. It's taken me so much time that I didn't have time to join in with the exciting developments with electrons. I have used electron microscopy, and it's obvious if you look into the scientific literature of the last year or two, there's a lot happening in work with electrons as the probe as well. There's been an evolution of the capability of the synchrotron, and that's come through very clearly in Sven's talk and Ronald's talk. Capabilities have changed a lot. In the early years, to a modern beamline scientist, when I describe the things in the first few slides, they're really very surprised at the low level of performance. But to me as a young man, it was so exciting, and I'll convey that to you why. The impact, we should always think about the impact, not as a slave to the impact, but we should always think about the impact. Is it important? I will give you a glimpse of when I first realized that what I was doing was important, because my father, my mother, my aunts and uncles and cousins could see from me being mentioned in Scientific American, maybe I was doing something good with my career, rather than them saying, when are you going to get a proper job? The need for neutrons comes from the interest in enzyme mechanism in particular, for which X-rays are very powerful. But neutrons add a whole new dimension because of the sensitivity to protons, and therefore proton transfer, and the role of water, not only as H2O, but as the OH minus or H3O plus. Amazing versatility of water in those chemical situations. Previous talks have emphasized small focal spots. My first machine, the synchrotron source at Daresbury, we had a source size 14 millimeters. This put experimental physicist that I was as a challenge, a big challenge to make focus onto my crystal of 300 micron, which in modern day is very big compared to micron. So things have changed a lot, but the start was very exciting nevertheless. Collimated X-ray beams onto the sample. Tunability of the wavelength. So you could do X-ray diffraction with spectroscopy. Sven talked with a particular example, and I'll show you some more. And these properties are very well suited to macromolecular crystallography. And there are special possibilities. We can use the full polychromatic emission, like Lowy, Friedrich Nipping and von Lowy, but now with a much more intense polychromatic beam, and we can measure very fast diffraction data. And there's a defined time structure that the machine naturally has with the picosecond bunches, and there's a plane polarized aspect to the property of the X-rays, which also gives possibilities. That is much more specialized, but there are possibilities. Now, how to set the context for you of neutron macromolecular crystallography. I mentioned the 14 millimeter synchrotron source size. Very primitive compared to today. But if you look at the 1972 Royal Society discussion meeting on study of enzymes, there was a talk from Dr. Sax Mason in Grenoble, who was the instrument scientist lead at the pioneering D19 instrument on the Institut Laval-Angevin. It had taken him 9 months to measure one data set on a single counter diffractometer. His crystal was 3 by 3 by 3 millimeters, so 27 millimeter cube. Quite a rare specimen, almost the size of the diamond of the 26th Congress of the Communist Party, which is in the museum downstairs. So this was a very primitive stage. Could we improve on it with the work we were doing at the Daresbury synchrotron with X-rays to transform this situation and combine with developments in Japan with improved neutron sensitive area detectors? So let's come in part one to look at the synchrotron radiation studies, and then I'll move on to the biological crystallography. The gentleman at the left there is Professor Michael Hart, who very distinguished synchrotron X-ray scientist and developer of X-ray monochromators. He became director of the Brookhaven National Synchrotron Light Source for a while. He produced this slide here, so this is a credit giving the proper citation to Michael. He wondered how to convey through the last century the change in capability of X-ray science. He thought he would compare it with computing power. We all know the major changes in computing power over the decades. That's this line. X-ray science developments completely dwarf the changes in computing power. It's this. So that gives you a feeling for the change of capability through the last 100 years. So much was the excitement in the scientific community, we could even set up, with the generous aid of the International Union of Crystallography, our own dedicated journal of synchrotron radiation, which we did in the mid-1990s. Samar Hasnain suggested the idea, and the IUCR involved myself and Hiromichi Kamitsubo from Japan. And these were all the sources that were operating at the time in the mid-90s. So we had sources, beamlines and optics, detectors, electronics and data acquisition, sample handling, and then 3 domains of science and technique: diffraction, spectroscopy, and imaging. Now, what about these early attempts of mine? I heard about first experiments going on at Stanford. I went to see the head of the lab. I want to go to Stanford in California. He said, you don't need to go to Stanford. You can go to the north of England, where they have, through the work of Ian Munro, the use of the high energy physics machine NINA, which he built a beamline in 1969. Why don't you go and try that? With a fellow PhD student, we owned a car. We kept the minimum amount of petrol in this car so that neither one of us could enjoy too much of the benefit over the other of the cost of putting a gallon of petrol in. From the lab, I took a precession film camera and a microscope and the chemicals to develop the photographic X-ray film. Off I went to the north of England and used the Nina beamline. I had 24 hours of beam and nothing worked, but my local contact, Professor Joan Bordas, and myself could see what was needed to develop to do the things I wanted to do. What did I want to do? I wanted to optimize the anomalous scattering, which we now call resonant scattering, and I wanted to deal with the particular problems of measuring protein crystal X-ray diffraction data. And there was a plan for a new dedicated X-ray source. I mentioned it on my first talk, the SRS at Daresbury. The first dedicated X-ray source for synchrotron in the world. So from virtually nothing, good ideas, and a plan was developed. I developed the plan for the new dedicated source for protein crystallography. This is the same diagram I showed the other day, where I showed applications. Now I'm showing particular instruments. So bending magnet 7, station 2, was the first experimental beamline that with my team we put together. And then on the Wiggler magnet, number 9, straight section, built another one, and then I built a third one. And then later, other colleagues developed this one here, for which from Manchester I did a crystal structure of the carotenoid protein. And then we built another beamline here, led by Samar Hasnain. We're also developing interest in solution scattering, which Joan Bordas had built a beamline here. And we used it for doing the alpha crystocyanin. That was the 8 of these in solution. We could get a model from the solution scattering patterns. And here is the Daresbury laboratory. This is a nuclear physics Van de Graaff generator. So that was another activity at Daresbury, nuclear physics. And the SRS was in here. And we were in the middle of the countryside, halfway between the University of Manchester and the University of Liverpool. These cities are great rivals if you follow the football. And this compromised location was to keep both Liverpool people and Manchester people happy. But it was a national facility. So here's a few details of the beamline design. We had a monochromator, so that is what extracts this very fine monochromatic beam that Sven alluded to. And we bent the monochromator to focus the beam horizontally, and we had a vertically focusing mirror here. And this is the source that we had at the time, 14 millimeters wide by 400 micron high. But I wanted to tune the wavelength, so it was important to rotate this monochromator about a vertical axis, and we had to move the instrument and the crystal to follow where the beam went. The emission, photons per second, etc., on the y-axis and the wavelength here, from the bending magnet and the superconducting wiggler were of this shape. With the monochromator in, you take a very fine wavelength band out, and by altering the angle, you move the wavelength that you select. And so I gradually did test experiments with these different monochromatic wavelengths over really quite a wide range. The whole thing was inspired by work at Stanford, which I learnt about from Dorothy Hodgkin, Nobel Prize in Chemistry. And my supervisor's supervisor was Dorothy Hodgkin. My supervisor was Margaret Adams. And this was the team: mechanical engineer, a scientist, a student, and experimental officer. Andy Thompson, now life science director, Soleil. Paul is at the Australian National University Chemistry Department. Trevor is a professor of structural biology at Keele University. Phil Moore, after working with us, he went to Hawaii to be the mechanical engineer building the infrared telescope at Mauna Kea in Hawaii. And here is our paper in the Journal of Physics E, 1982. That's more than 10 years before the Journal of Synchrotron Radiation was launched, and so it was in this General Physics journal here. So, even though the initial SRS was not well suited to crystallography, especially with its horizontal source size of 14 millimeters, initially I could get 20 times the home lab intensity and was fully tunable. The addition of the vertically focusing mirror brought us up to 100 times the best home lab intensity. Great excitement. Today, Sven showed that you're looking at some million times more intensity at the sample, at the synchrotron. At this time, in the early 80s, we were 100 times better than the home lab. It still was fantastically interesting, and we got the first users. Of course, we had our own ideas, my own ideas for using it, but the UK users and the international users were very interested, and we got exciting results. So in the UK, this was my supervisor, Margaret, and these were the lab leaders around the country: Oxford, London and Cambridge. David was at both places for a while. Oxford, Birkbeck College, London, Sheffield. From Sweden, the groups came, and from the US, great interest. We were ahead of the US. From a point where we were behind the US, me, as a graduate student, early postdoc, I'd brought the UK ahead of the US. That's a great feeling. Trust your feelings. One of the projects, this one that my relatives were interested in, Scientific American quoted my role in the project. Sorry. We had Steve Illick and Charlie Bugg, the academics from Alabama. They brought the crystals, we measured the diffraction data and included heavy atom derivatives. We could get the electron density map. This is the full unit cell. You see 90,000 molecular weight here, and it's just a small area of interaction holding the crystal together and a large solvent channel here. We could see the helices. We could interpret each one of these. Here's the trimer, and we had therefore the full enzyme structure. This was a very important enzyme to inhibit for a medical treatment, and Charlie Bugg here set up a company, BioCris Pharmaceuticals, on the basis of this structure. And that's why the article he wrote in Scientific American is called Drugs by Design. So the role of three-dimensional structure to guide design of new chemical compounds for drugs emerged on the scene. A second application was distinguishing elements close in atomic number. Sven gave a really nice example. It was 1 electron difference, atomic number difference 1. The project here involves a protein like the concanavalin A, but from garden peas. It has a similar shape. It involves manganese and calcium, and this was earlier than the work I showed the other day, and it was to distinguish which was manganese, which was calcium. And so from these optimized anomalous scattering data, we could see explicitly which was calcium, which was manganese, and the two subunits, one subunit here and the other subunit there. And the experiment was led by Howard Einspar. So visiting scientists, I'm the beamline scientist helping use the instrument. From Stanford itself, the people there were very interested in our Wiggler beamline and the use of microcrystals with the X-ray diffraction. We used the white beam focused onto a sample of gramicidin to simulate the sort of intensities that we would have at the third generation undulator, which I'll come on to in a moment. And we could see very good diffraction spots from a sample of 20 microns in size. So at this point, I was leading the working group for the European synchrotron macromolecular crystallography. And this was very, very important because it told me that we could propose on the ESRF microfocus protein crystallography. Around this time, people were crystallizing whole viruses. And one of the leaders, Michael Rossman, he came to Daresbury and worked with me on the common cold virus, known as rhinovirus. And this is the acknowledgement that he gave, not only for using our beamline in Daresbury, but also in Hamburg in Germany, and he also took the crystals to the Cornell synchrotron. So this was actually great, but we became facilitators of what became the final data set measured in America in Cornell, and the structure shown here was published in Nature. The work on the Wiggler beamline was incredibly stimulating for various reasons. It wasn't only protein work, but I could also take white beam Lowry diffraction photographs from a protein crystal, in fact from a crystal that the user had left behind. I also started doing chemical crystallography work, collaboration with Marjorie Harding, a leading chemical crystallographer in the UK of the time. And we were also breaking new ground, moving away from photographic film to electronic detectors. And this gentleman here, Uli Arndt from Cambridge, had developed a prototype television detector that was commercialized by NRAF Nonius, and we bought one of the first TV diffractometers. Because of the polarization, we turned the diffractometer on its side so we could measure data in the vertical plane. And so home lab TV diffractometer installations would measure data in the detector moving in the horizontal plane. And this is my colleague that had joined me from the University of Leeds, Miroslav Papis, dedicated to developing experiments on the TV diffractometer. The virus crystallography made us very famous. The BBC News showed a picture of the foot and mouth disease virus, which was data collected on 9.6 by David Stewart and his team. From Harvard, Steve Harrison, Bob Lidington came, and they published the structure of this much larger virus, the SV40. And chemists were very interested too, because we could measure data to very high diffraction resolution. And I showed this the other day, so I won't dwell on it, but we got very finely detailed, well-resolved details of the sugar binding sites. And this is a journal, ChemCom, which is difficult to get published in, let alone to get the front cover, which we did. Detectors were a big challenge. So how to convey to you the rate of change of detectors. This shows a timeline from when we started at the SRS, early 80s, with film, up to when the SRS closed to hand over to Diamond, which is a new national synchrotron in the UK. So we had the TV diffractometer here on 9.6. There was development from Japan, image plates, and this was one manufacturer. And we had the charge couple device, and this is a different manufacturer. This was from Germany, this one was from the US. So we're having to be very flexible, not only in the type of technology to harness the better detectors, but also the companies. So here's a list of, in the 20 years, 79 to 99, of who I worked with. The company NRAF Nonius, the Rutherford Lab, sister laboratory to Daresbury, developing a multi-wire proportional chamber. Rigaku from Japan for an image plate system, an alternative to the German image plate system. Academic colleague Nigel Allinson for a different type of CCD, and ESRF had its own type of detector, an image intensifier CCD. An advanced photon source in the US likewise worked with Brucker to have their own CCD. In Ronald's talk this morning, you heard about the Pixel device from Switzerland with silicon, its successor, the cadmium telluride device, its most recent device. So there's been a lot of effort on trying to improve detectors. So that's a quick snapshot of the second generation source, SRS, pioneering, yes, but primitive by modern standards in its specification. We knew that at the time, and in Europe we had a fantastic collaboration between all the countries, and we came forward with a so-called foundation phase report in 1987, specifying the first of the third generation source. The US was not inactive, it was very active, and there was a workshop in Stanford on using the PEP high energy physics machine, which was 2 miles in circumference, to create an alternative way of getting to the third generation source. But the ESRF in Grenoble was the pioneer. The ESRF emittance, the source size that was available, was much, much, much better. And it was a much larger circumference. So we could use this undulator type of device, which we couldn't use on the SRS, certainly in the X-ray range. And here's a visualization of the emission from an undulator. So you have these very gentle undulations. So the emission from one peak catches up with the emission of an electron at the next peak. Now it's a relatively slow catch-up. The electrons are very near to the speed of light. The light is going that bit faster. You create the condition for an interference, and you have the polychromatic emission collapses into these individual emission lines. By altering the gap in the undulator, you can move the emission of the undulator through this envelope of the primary the first harmonic, the third harmonic, and so on. The Benny magnet emission is like at SRS, but much stronger intensity, and the wiggler is like the SRS, but much stronger intensity. So these numbers here on the y-axis, these are colossal increases over what the SRS could give. And these were at the time of the foundation. They improved a lot over the years, and now ESRF is shut down to make the extremely bright source. And I'll comment on that shortly. I mentioned the ESRF is based in Grenoble. It wasn't always so. There was a plan to put it in Strasbourg, a plan to put it in Trieste, a plan for Dortmund, a plan for Daresbury. Eventually, the decision, because this was a slow business deciding the site, was settled because Grenoble already had a neutron reactor. If we put the two near to each other, the synergies would be very good for scientists. And that became the decision. And the knowledge that was gained at ESRF helped improve also the national facilities, whether it was Diamond in the UK, Soleil in France, the Swiss light source, and so on. The US, 2 years after the ESRF, came on with its own third generation source, and 2 years after that, the Japanese. So there was a constant striving to keep ahead of the competition. Impact. What has been the impact? In this single image, you see the growth of depositions in the protein data bank. Sven showed 1 month's deposition. The fraction that is synchrotron is nearly all of them now. Before the third generation source, we were less effective than the home lab. We had tremendous potential and we could solve technically specialized things. But the ESRF and the APS and the Spring 8, these three third generation sources now dominate, and the ones that follow dominate all of the X-ray crystal structure determination. So we have 150,000 protein structures. The first one took 30 years to do. Now we have 150,000, and we add 10,000 a year approximately. The other things, ESRF allowed very fast measurements, and I showed this in detail the other day, so I won't spend too much time on it, but we could look directly at the changes of the electron density in the active site of this enzyme as it was fed substrate. So there's a fantastic change in mindset. We're not three-dimensional anymore, with 4 dimensions. Some things won't crystallize with the best will in the world, and we have to work either in solution or on electron microscope grids, or we can look to our crystal lattice to give clues for how things might assemble. And so this just showed, as I showed the other day, what we can do with small angle X-ray solution scattering, what we could do 5 years ago with electron microscopy. It's improved a lot since then. And what we can do by looking at our crystal lattice, and we can see similarities, and we can try and fit the solution X-ray scattering curve with these different models. These are called lower resolution techniques, and they give you a feeling for overall shape. And EM in particular, by using liquid nitrogen, liquid ethane temperatures, is now actually reaching atomic resolution for things that you can't crystallize. How far it will go is a matter of open debate in the field. Things like distinguishing metal atoms with the X-ray wavelength tuning is believed to be out of reach of cryo-electron microscopy. The cryo temperature anyway is well away from physiological temperature, so you have to worry about artifacts. So it's wonderful to get a detailed structure from cryo-electron microscopy if you can't crystallize it, but you're going to have to be careful in the interpretations and the assumptions in the way I mentioned, which is alteration of metal atom oxidation state and being at the wrong temperature for physiological interpretation. So in a slide, what can we say of today with synchrotron sources? The ESRF is upgrading to an extremely bright source. The third generation national sources are thinking about their upgrade. So there is a Diamond 2, for example. And in Lund, Max 4 has pioneered a new magnet lattice for extremely low emittance. The question arises, are these sources too bright for crystallography? And interestingly, not all the national sources are racing to make an upgraded lattice. So in Spain and France, at the moment, they're sticking with what they have. But to be fair, ESRF's extremely bright source will include a new beamline for time-resolved microsecond monochromatic macromolecular crystallography, and it's a method called serial femtosecond crystallography, coming from the new X-ray lasers. But they will do microsecond monochromatic work with that. I think in the whole domain of synchrotron crystallography, a highly impressive beamline is at Diamond, led by Dr. Armin Wagner, and he is targeting the lower atomic number elements. So if we take chlorine as an example, we see in these two curves here the variation of the real and imaginary components of the resonant scattering of chlorine. And there are particularly big changes here at around 4.5 angstrom wavelength. So by using wavelengths either side of here, like the manganese calcium experiment before, we can discriminate, is a peak a chlorine or might it be something else? But the wavelength, 4.5 angstrom, is absorbed by air. So you've got to put the diffractometer in vacuum. It's not easy. So this is a type of detector also manufactured by Dectris in Switzerland, and it can sit in vacuum, remove the X-ray absorption problem, and you measure the diffraction data at these very long wavelengths. And there's a great potential for this area because the assignment of low Z ions in biological structures can be very problematic because of working so far away, typically from the absorption edges. If you want to distinguish magnesium and phosphorus and chlorine, could be particularly important for function. You need to be proving that the peaks in your electron density map are one element or another. Now let's make the transfer to consider the neutrons. I showed this the other day, I won't spend too much time on it, but the neutron scattering is quite distinct and different from the X-ray scattering, and hydrogen is negative to neutrons and deuterium, its isotope, is positive. So the contrast variation between these two is a very powerful technique in neutron scattering. And in neutron biological crystallography, this being a very large value gives great scope for locating proton, but as a deuterium, hydrogen as a deuterium. So you can make a complete description of your biological molecule, including the hydrogens. You can measure at room temperature because the radiation damage is absent. Therefore, you are close to physiological temperature. It is perfect. But the fluxes are low. And so the last 20 years, the work has all been of a technical nature to try to make the technique more efficient. Also, you have to start with a structure that's come from X-ray crystallography or now from cryo-electron microscopy. You don't solve the structure using the neutron data alone. 20 years. We have more instruments, we have shorter measuring times, not the 9 months of 1972, not a small protein of 1972, much larger proteins and much smaller crystals being viable. It's changed a lot. Software development for the use of the polychromatic beam, we use the X-ray synchrotron Lowy software. And it took many, many years of development, and it was transferred to Grenoble and other neutron centers around the world. It's a very complete software package that's proved quite popular from the X-ray work. In Grenoble, my former student, Matthew, is in charge of this instrument, the Lowy diffractometer, and I think I showed this in a slightly different picture the other day. The new information is here. So the crystal volumes that we're working with now, not 27 millimeter cube, but for a small protein of the size of the lysozyme, we're down at 0.05 millimeter cube. And we can go all the way up to 93,000 molecular weight quite readily. It's a massive change in capability. We can see, I showed this the other day, so I'll be quick. We can see the deuteriums on the histidine. We can see what the different ionization states can be for these sort of amino acids. So what are the limits for neutron protein crystallography? These red squares are the recent measurements made on the Lowy diffractometer Grenoble. We're moving to smaller crystal volumes and larger molecular weight proteins. The community has woken up. The days requested divided by the days available is a major overload. So there's a big queue of people wanting to use this sort of instrument. In Lund, in Sweden, is the European Spallation neutron source. And this is a different type of neutron source. So you push protons into a target, Mercury, and the emission of the neutrons comes in pulses. So each pulse of protons into the target, you get out a pulse of neutrons. And they're of a white polychromatic nature. Naturally, Lowy diffraction at the reactor, Lowy diffraction at the synchrotron are synergistic. So here's the neutron macromolecular crystallography at the ESS team here, which is led by Esko Oksanen. I'm chair of the Scientific and Technical Advisory Panel. Here's a computer-aided design picture. Here's a generic person of 6 feet high, let's say, 2 meters. The sample sits here. The detectors are placed by robots. And it's a very flexible instrument design. The reactor LADI instrument is rather inflexible in design. So we're going for a flexible design. This is Dorothea Pfeiffer from CERN detector group. So she's working with the ESS team on a new type of neutron-sensitive detector. And Dorothea and Richard Hall-Wilton from the ESS detector group were testing this new detector at the neutron source, I think in Norway, the neutron source. So this is a very exciting development. To evaluate its capability, this is using the Daresbury synchrotron software, using a test sample that is a project at the University of Aarhus in Denmark, very large unit cell, very congested diffraction pattern, and we can predict all the different diffraction spots and their wavelengths and their indexing for the whole pattern. And more than that, we can look at the time of flight of arrival of the diffraction spots at the detector. So this is zooming in to a small portion of that very large area diffraction pattern. And we can see that the time of arrival of this diffraction spot, 73.3 milliseconds, and the one here is 3 milliseconds later. So you can actually see both in space and time where the diffraction spots are appearing and when they will arrive because of the nature of the spallation neutron source. So from the measurement physics point of view, we have the ideal situation of minimizing the background noise underneath the signal reflection intensity. So this is a very powerful tool that has been developed in Lund for this sort of unit cell, very large protein unit cell. There are many instruments being developed on the ESS, like all of these facilities, power diffraction, small angle neutron scattering, and the like, imaging. So this is one of a whole suite of instruments. So if we look at the worldwide snapshot of the PDB, like we did for the X-ray structures, what is going on? So with calendar year here, and the molecular weight of the protein, we see gradually many more proteins are being studied, and they're going to much larger molecular weight. You would say, compared to 150,000 X-ray structures, this is a tiny number. But the point is that each one of these has solved some structural biology science question that had been unsolved with X-rays, electrons, or NMR. To get beam time, these other techniques have to have failed because they're the easier ones to apply first. Then you try the neutrons. So it's really a massive impact in scientific research, structural-based scientific research, if you have a neutron structure. We held an international workshop at the European Crystallography meeting, ECM, in Oviedo, Spain, last summer. And there are new facility also in Germany at Jülich, and we had representation from Jülich, ESS, Grenoble, and myself chairing the organizing committee. We had about 50 scientists from around the world. So this was the first meeting outside of a neutron facility. Impact. Another impact is industrial applications. The other day I emphasized this, so I won't spend too much time. But pharmaceuticals is one area, but also material science is another very strong activity. Daresbury, ESRF, about 10% of the usage is for industrial applications. Australia and Canada light sources have increased beyond 10%. Canada in particular, I think, is up to about 20% of its usage is with industrial projects and industrial collaboration. So to conclude, the last 30 years has seen a revolution of capability of synchrotron radiation macromolecular crystallography, and the last 10 years has seen a steady improved provision of the neutron macromolecular crystallography centers worldwide, and completely revived the field of neutron work in biological crystallography. I did not have time to discuss the X-ray laser. I've done relatively little with the X-ray lasers anyway, and I couldn't really talk with personal experience. The XFEL approach developed the serial femtosecond crystallography, which ESRF is adopting now in its extremely bright source, one of its beamline developments. The X-ray laser, in its second generation at Stanford and in the generation at Hamburg, there is the possibility, still not clear it will be achieved, of single molecule diffraction. So this is an incredible thing that you would not, in that concept, need the amplification of multiple molecules in a crystal. So it's a really, would be an amazing thing to be able to work with single molecules, sufficient diffraction strength. It would be room temperature, no radiation damage, and the sample, of course, is destroyed immediately after the recording of the diffraction pattern, but you don't mind that because you've got the information you want. And so if it would be possible, the single molecule X-ray laser diffraction would be better than the cryo-EM because it would not need the crystal, and it would be at the physiological temperature, and there would not be radiation damage. So this is a pot of gold that is in the minds of the X-ray laser community to try to realize, and so you must watch for that possibility. We don't know if it will work yet, but it's an amazing concept, which is particularly from a researcher in Sweden, Uppsala, Janos Haidu. I gave this acknowledgement the other day, so it's the same slide. I show you a collection of different books. I seem to enjoy also writing books. There are many hours in the week, it seems. So anyway, there we are. Thank you very much. It is a question discussed in the field. If you do some comparisons of an X-ray crystal structure, which is now also done by cryo-EM, and you can find a paper that's evaluated quite a number of them in that way, you find a lot of problems with the cryo-EM structures. What is said is that the validation procedures for X-ray work are more well understood, and the ones for cryo-EM are not, and it will improve. But it is also true that for things like metalloproteins, the impact of the electron beam on the metal is at the moment not investigated, and probably is going to be a big problem. A third of a genome is metalloprotein. And you've got this temperature artifact question, which we already know by comparing room temperature protein crystal structures with X-ray and cryo protein crystal structures with X-ray. You get structural changes, particularly movement of water molecules. Secondly, also radiation damage. So I think what's going to happen is if you can't get a crystal, then you're going to be very pleased with what you can get with cryo-EM. If you do in the end get a crystal, then I think you would not resist, you would want to do the X-ray crystal structure anyway. And after all, if you think about the basics, with one technique you can be precise. With two or more techniques you can be accurate.
precise, вы очень воспроизводимо что-то делаете, но при этом может быть далеко. И вот эти два термина очень важно различать, потому что просто языке тоже есть разные слова, но мы говорим точность, а точность она бывает совершенно разная. В статистике для тех журналистов, по такому языке решаем вместе, хотя для исследования это принципиально разные вещи. Ну и был вопрос насчет первой практики. Если не удается закристаллизовать и делать нечего, приходится электронной микроскопии, это замораживание, неестественно. Кристаллы до сих пор тоже замораживают, иначе они горят. А лазер позволяет снимать кристаллы в комнате, кто-то представляет консольную картину. Вот это открывает то, чего раньше не было, сейчас появится. Ну и лекция в конце говорилась о том, что еще одна новая сверхзадача, которую поставили, это обходиться без кристаллизации, изучать дифракцию отдельного момента. Это можно только говорить электронно, это точно начинает заниматься. Непонятно, что из этого получится, но скорее всего получится. Это будет действительно.
So as an example, the alpha crustacyanin, which is the eight of the beta crustacyanins, we could not grow quality enough crystals of the alpha crustacyanin. It's 1/3 of a million molecular weight, and so I think we had 10 angstrom resolution diffraction spots, but we couldn't get a unit cell even, and so that's why we turned to EM and solution X-ray scattering and came up with these models. And then after this time, the cryo-EM improved quite a lot. Why did the cryo-EM improve? When the electron beam hits a sample, it jitters. And with the CCD in the electron microscope, you do the framing of the imaging, and then you combine the frames, slightly altering the alignment to take away the jitter, and that was a major breakthrough of using the fast CCD detector for electron detection in electron microscopy. That gave a major part of the breakthrough. Another point that is emphasized by cryo-EM specialists is they need less material than trying to screen conditions to grow crystals. So that's also an important point, of course. If you're not able to purify or express a lot of protein, the cryo-EM uses less than the crystallization. So it's an interesting time for, there is obviously an alteration of the balance of power for structure determination. That is true.
Conclusion, что сейчас очень интересное время, потому что в макромолекулярной биокристаллографии сейчас в каком-то смысле слом методов, переход к совершенно новым методам. Ну и криоэлектронная микроскопия, очень мало вещества расходует, это большое преимущество. И сейчас большой успех достигнут потому, что научились, перейдя к новым телевизионным детекторам, CCD-детекторам, решать проблему, которая возникает из-за того, что пучок, когда контактирует с хромосомой, образец начинает смещаться, и смещение улучшает качество данных. А с новым очень быстрым детектором теперь можно получить много-много фреймов, потом каждый из них как бы перефокусировать и получить новый набор уже программный, которым эта проблема решена. Ну и дальше там еще перечисляют разные технические решения, но главное, что именно в это время, вот сейчас, эти годы, начинается революция методов исследования этих объектов. То есть то, что долго развивалось медленно и поступательно, сейчас начинает развиваться скачками, и буквально несколько лет могут изменить совершенно наш подход. Другая кристаллография прошла через это в начале века, 21-го, когда появились двухкоординатные детекторы, там была мини-революция. А в макромолекулярной она наиболее активную фазу переживает сейчас. Свен, вы сказать,
Yes, I would like to return to the question you got before about cryo-EM and X-ray diffraction, because there was a similar discussion 15 years ago, whether X-ray diffraction would disappear and be replaced by NMR, or if the reverse would happen. And clearly, when it comes to structure determination, X-ray diffraction has won out over NMR, but we still see a lot of NMR machines all over the world for macromolecular applications. So please comment on this.
So the NMR area is nuclear magnetic resonance. I alluded to the other day in response to a question from Dima. The method is particularly suited for understanding dynamics, and so the titration of ionizable amino acids is you can study, and also the exchange of water molecules can be studied directly by the NMR. So you get a feeling for the dynamics of the structure. And that is harder with diffraction methods. So there is that complementarity. But what Sven is alluding to is that 15 years ago, there was very much a feeling within the NMR community that they could also replace crystallography because you could do the structure in solution without having to crystallize it. In the protein data bank, you can find structures that you're trying to crystallize are available from NMR. In general, they are the smaller proteins. The NMR specialist argues that actually you can get to larger, but the preponderance of structures seems to be smaller ones. It's obviously a very powerful technique in structural biology, and it is making major contributions to the PDB. But the predominant driver for new structures in the PDB, is synchrotron X-ray crystallography. That's what the data show us.
Комьюнити считает, что фракция это будет, фракция считает, что МР это будет. А в действительности то и другое дополняет друг друга, но пока что при помощи МР делаются больше более мелкие молекулы. А в фракции есть один минус, что надо закристаллизовать, прежде чем проводить эксперимент. Но это на самом деле преодолевается, потому что все меньше и меньше необходимым условием становится наличие кристаллов. May I also add a question? I attended a school in H where Professor Schreier, I think, from Chicago, was showing examples how they are using X-ray 3 electron laser to follow reactions, proteins directly into the cell, such as oxidation or reactions with CO2. And they didn't need crystallization, and because of the extremely high rate, they could make a movement of the reaction of the protein in the cell. It sounded absolutely fantastic. So maybe this is one of the directions where
What spatial resolution was that? I'm not knowing the exact study that you refer to. There is one I will mention in a second, but what resolution were they? But it was a whole cell. Yeah, I think it's probably several hundred angstrom resolution. So that sort of domain of resolution, you can see blobs. You get a feeling for where the whole entity is, but not any chemical details.
And what about this experiment done in couple cells?
I think it's the same sort of spatial resolution. I mean, in terms of chemistry at the femtosecond time resolution scale, the very exciting project area of the moment is from photosynthesis. So there's a complex in the membrane called a photosystem, which takes the light and splits water, and you derive energy. And the heart of the large protein molecule is a manganese calcium metal cluster, which is called the oxygen evolving complex. Many years ago, a gentleman by the name of Dr. Koch elaborated the Koch cycle, where pulses of light would alter in a cycle the oxidation states of the manganese. Manganese, as you know, is very flexible with its oxidation states. Going through the 0, 1, 2, 3, 4 states, which are called S states, which go on timescales of tens of femtosecond to a bit slower, but you can, with the X-ray laser, which is giving you femtosecond X-ray diffraction time resolution, study these S states. You want chemical resolution, you need to have a crystal. So you flow crystals past a laser to give it a light flash, and then the X-ray laser to get the information. And every 6 months is a new study from either Stanford or Japan, and there will be from Hamburg, and gradually they're developing the spatial resolution now, most recently to 2 angstrom resolution, and the sophistication of combining the spectroscopy and the diffraction and stimulating the oxidation states of the manganese. They're gradually working out the structural details of this cycle of the oxygen evolving complex. It's fundamental structural biochemistry, the fundamentals of life, but it has huge possible potential for an energy source, because if you've separated water into hydrogen and oxygen, you've got a fuel source. So if you could find a way to mimic that process, your car, you just put water into the tank, and then you create steam instead of pollution. Anyway, that's where perhaps too vivid an imagination of how a discovery might change things, but it is clearly a fantastically interesting natural system with technology potential.
Естественно, каждый кристалл сгорает после того, как он полетает, а вот поток кристаллов летит. Освещаясь лазером, который вызывает фотосинтез, изучение механизма фотосинтеза искусственного, рентгеновский лазер, в это же время, в этом же образце получает мгновенный снимок структуры, искусственного состояния, окружения соответствующего этому моменту. Ну и вот тысячи кристаллов, которые полетают в короткий промежуток времени, дают терабайты информации, которые потом можно обрабатывать. Но кроме того, что это фантастическая возможность снять фотосинтез, это, конечно, большая практическая перспектива на источник энергии, фото расщепление вакуума. Естественно, вот эти вещи сегодня делаются, каждые 6 месяцев появляется какая-то публикация. Но тема эксперимента эти безумно сложные, безумно дорогие, но и фантастически интересные. Это вот те новые техники, которые есть. На одном полюсе старое оборудование, которое мы эксплуатируем за 50-60 лет, и не только мы основное, но продолжает работать, и оно решает свои задачи. Но одновременно с этим развиваются совершенно космические технологии у нас на Земле. Мне хотелось, чтобы они хотя бы узнали. А кроме того, у нас есть доступ к лазерам свободного гамма. У нас есть право использоваться. Россия 25% стоимости строительства этого лазера. И не хватает людей, которые будут писать грамотные заявки, которые пройдут использование и получат шанс на то, чтобы. То есть не надо думать, что это все не досягаемо. Это досягаемо. То есть надо уметь этим пользоваться. Any more questions? If there are no more questions, thank you once again.